The Feynman Lecture on Physics, Atoms in Motion, 101, Introduction. This 2-year course in physics is presented from the point of view that you, the reader, are going to be a physicist. That is not necessarily the case, of course, but it is what every professor in every subject assumes. If you're going to be a physicist, you will have to study a lot. 200 years in the most rapidly developing field of knowledge that there is. So much knowledge, in fact, that you might not think you can learn all of it in 4 years. And you truly cannot. You will have to go to graduate school as well. Surprisingly enough, in spite of the tremendous amount of work that has been done for all this time, it is possible to condense the enormous mass of results to a large extent. That is, to find laws, which summarize all our knowledge. Even so, the laws are so hard to grasp that it is unfair to you to start exploring this tremendous subject without some kind of map or outline of the relationship of one part of any subject of science to another. Following these preliminary remarks, the first 3 chapters will therefore outline the relationship of physics to the rest of the sciences, the relationship of the sciences to each other, and the meaning of science to help us develop a feel of each subject. You might ask why we cannot teach physics by just giving the basic laws on page 1 and then showing how they work in all possible circumstances, as we do in Euclidean geometry, where we state the axioms and then make all sorts of deductions. So, not satisfied to learn in physics in 4 years, you want to learn it in 4 minutes. We cannot do it this way for 2 reasons. First, we do not yet know all the basic laws. There's an expanding frontier of ignorance. Second, the correct statement of the laws of physics involves some very unfamiliar ideas which require advanced mathematics for the description. Therefore, one needs a considerable amount of preparatory training to learn what the words mean. No, it is not possible to do it that way. We can only do it piece by piece. Each piece or part of the whole of nature is always merely an approximation to the complete truth, or complete truth is so far as we know it. In fact, everything we know is only some kind of approximation because we do not know all the laws as of yet. Therefore, things must be learned only to be unlearned again, or more likely to be corrected. The principle of science, the definition almost, is the following. The test of all knowledge is experiment. Experiment is the sole judge of scientific truth. But what is the source of knowledge? Where do the laws that are to be tested come from? Experiment itself helps produce these laws in the sense that it gives us hints, but also needed is imagination, to create from these hints the great generalizations, to guess at the wonderful, simple, but very strange patterns beneath them all, and then to experiment to check again whether we have made the right guess. This imagining process is so difficult that there is a division of labor in physics. There is a theoretical physicist who imagine, deduce, and guess at new laws, but do not experiment, and there is experimental physicists who experiment, imagine, deduce, and guess. We said that the laws of nature are approximate, that we first find the wrong ones and then we find the right ones. Now, how can experiment be wrong? First, in trivial way, if something is wrong with your apparatus that you did not notice, but these things are easily fixed and checked back and forth, so without snatching at such minor things, how can the results of an experiment be wrong? Only by being inaccurate. For example, the mass of an object never seems to change. A spinning top has the same weight as a still one, so a law was invented. Mass is constant, independent of speed. That law is now found to be incorrect. Mass is found to increase with velocity, but appreciable increases require velocities near that of light. A true law is, if an object moves at the speed of less than 100 miles a second, the mass is constant to within 1 part in a million. In some such approximate form, this is a correct law. So in practice, one might think that the new laws make no difference. Well, yes and no. For ordinary speeds, we can certainly forget it and use a simple constant mass law as a good approximation. But for high speeds, we are wrong. The higher the speed, the more wrong we are. Finally, and most interesting, philosophically, we are completely wrong with the approximate law. Our entire picture of the world has to be altered even though the mass changes only by a little bit. This is a very peculiar thing about the philosophy of ideas behind the laws. Even a very small effect sometimes requires profound changes in our ideas. Now, what should we teach first? Should we teach the correct but unfamiliar law with its strange and difficult conceptual ideas, but, for example, the theory of relativity, 4-dimensional spacetime, and so on? Or should we first teach the simple constant mass law, which is only approximate, but does not involve such difficult ideas? The first is more exciting, wonderful, and more fun, but the second is easier to get at first. and is a first step to a real understanding of the second idea. This point arises again and again in teaching physics. At different times we shall have to resolve it in different ways, but at each stage it's worth learning what it is now known, how accurate it is, how it fits into everything else, and how it may be changed when we learn more. Let us now proceed with our outline, or a general map, of our understanding of science today, in particular physics but also other sciences on the periphery, so that when we later concentrate on some particular point we will have some idea of the background, why that particular point is interesting, and how it fits into the big structure. So what is our overall picture of the world? Next we will cover matter is made of atoms.